Hi all, today we are going to discuss about permanent magnet moving coil type of instruments which are also called as PMMC instruments. So this is the most accurate instrument for measurement of particularly DC current and the voltage, and the basic working principle is same as that of the D-Arson-Wall type of galvanometer. So only difference will be there in this PMMC type of instruments. There will be pointer and a scale system will be there, whereas in the case of D-Arson-Wall type of instrument or D-Arson-Wall meter, so there will be a mirror will be used for doing the measurement. So that we will discuss in the coming lectures. So only basic thing I want to tell, the basic working principle for this one is based on D-Arson-Wall type of galvanometer only. So then coming to the working principle, because we know that whenever a current carrying conductor is placed in a magnetic field, it will experience as a force which tends to move it out of the magnetic field. So that is a basic working principle for this one. So in order to understand that, so I am taking a north pole and a south pole. We know that the magnetic flux will pass from the north pole to the south pole. You agree with me? So now let us assume the current is passing in the conductor. There are two conductors. This conductor, let us take it as a dot. Dot means current is coming towards us, and the cross means current is going away from us. So whenever the current is passing through a conductor, the direction of the magnetic field can be found by using the right hand thumb rule, where if your thumb is indicating the direction of the current, then your curled finger will indicate the direction of the magnetic field, and vice versa. If it is like a coil, if your curled finger is indicating the direction of the current, then your thumb indicates the direction of the magnetic field. So in this case I am taking this single conductor, so around this I want to find how the current will come. So current will encircle this one, so the current will encircle this one in this way. So similarly here also the current will encircle here. So the direction of the magnetic field you can find by your right hand thumb rule. Hold your thumb in such a way, first one is dot, that means thumb will point towards us. Your curled finger will indicate in the counterclockwise direction. So this is the direction of the magnetic field. Agree with me? So similarly for the second one, as the current is going inside, so the direction of the field will be coming like this. So now from the north pole, whenever the field is passing, let us take with a different color. So here the field is passing like this, but here you can see whenever the flux is coming like this, here you can see this, here the flux is opposing, and in the lower side the flux is in the same direction as the flux that is passing from the north pole. Agree with me? So we can tell that in the upper side, as the flux, both the fluxes are in the opposite direction, they will cancel each other or a net magnetic field is decreased, whereas in the lower side the resultant magnetic field is increased, and here there is a cross magnetization effect. There is one magnetic field like this, one magnetic field going downwards, or otherwise, so in other sense we can tell that if you are writing the magnetic field or drawing the resultant magnetic field, the resultant magnetic field will come like this. So it will be passing like this, and at this point the current, because this conductor is opposing the passage of the flux, so here this side the flux is adding, and here again you can see this flux is opposing here, and this side it will be adding. So the flux will pass like this, so it will pass in this manner. So this side the flux is adding and the second side the flux is decreasing. So this way the flux will pass. So we know that always our magnetic field want to pass in the straight line. So how this flux will pass in the straight line? So it should push this conductor upwards. That means it should push this conductor like this, and similarly this conductor should move downwards. So when this conductor is moving downwards and this conductor upwards, it will produce the rotation. That means the rotor will rotate such that the flux will become a straight line. This is the basic working principle. So if you are confusing here, so the second alternative way how it can explain is using the Fleming's left hand rule, which states that if you are holding your left hand in such a way, the three fingers are perpendicular to each other. If your middle finger indicates the direction of the current, because in this case the dot is my direction of the current, that means it is coming towards us. So middle finger you can point towards us as displayed here. Then B is the direction of the magnetic field. We know the direction of magnetic field will be from north pole to south pole, so I have kept it properly. So this F indicates the direction of the force. So the force that is exerted on this conductor will be in the upward direction. Similarly in this conductor, because you know it is cross means it is going away, you can just reverse your hand in such a way. Now your middle finger will point inwards and your pointing finger will indicate from left to right, then your thumb will indicate downwards. So that's why the force will be downwards. So the amount of the force that is produced will be is given by B into I into L. So if you want to know how this come and other things, these are explained in electromagnetic field theory course. You can please refer there in the electromagnetic field theory playlist. So now where B is the flux density in the air gap, which is in Webers per meter square, and L is the effective length of the conductor which is lying inside the magnetic field, and I is the current passing through the conductor. So because of this, what happens, the force is produced, the rotor will start rotating. So if you are keeping your force the straight line like this, you can see here the gap is less, but as you are going away the gap is increasing. So when the gap is increased, so automatically the flux density, because gap is more, automatically the flux will decrease or the flux density will decrease. So in order to produce the uniform torque, that means same torque irrespective of what is the location of the conductor within the magnetic field area, the pole should also have the same shape as your rotor. That means it should have the concentric cylindrical shape. It would have the concentric circle which should be in the similar way. That means we have to extend this pole in such a way that it will be concentric with this one, so that the flux that is passing at every point will be radial. It will pass from your north pole to the rotor radially. So every point the flux is perpendicular to the conductor motion and it is having the same value of B. So for that purpose it should be designed like that. So that means practically I should be like that. It should be concentric circle. It will be in the circular shape like this one. So practically if you are deriving for the practical case, so it will be like this. There is a pole which will be the permanent magnets will be there. So in between there will be some core will be there in the center, because whenever the flux is passing, I want to produce the low reluctance path. So in order to provide the low reluctance path, generally the core is made up of soft iron. So soft iron core will be there. So above this core we will keep some frame, that means aluminum frame, which is used for damping also, and above that we make the winding of the coil. This is the coil that is wound. So now I am representing B is the flux density in the air gap in Webers per meter square, I is the current in the coil, L is the effective axial length of the coil, and let B is the breadth of the coil. Breadth of the coil means it is the distance from this point to this point. So this is nothing but equal to B. B is nothing but 2 times the radius of this coil. Radius, that means from center to one side coil, what is the distance, multiplied by 2, that is equal to B. So N is the number of turns of the coil. That means instead of one conductor we are keeping a coil, multiple turn coil. So multiple conductors are lying here. So now force on one side of each coil, that means each side of this coil will be equal to, we have already seen it is B into I into L, and total N conductors are there. So they will add to each other. So total force will be B into I into L into N, that much newtons will be there. So torque produced on each side of the coil, because we know torque is equal to force multiplied by radius. Here because the diameter is equal to B, so automatically radius will be equal to B by 2. So now if you want to calculate the total deflecting torque, because we have seen that 2 torques will be produced, one torque will be produced because of this one, another torque will be produced because of this one. Let us assume, so because of this one the torque is produced here, similarly here also some another torque is produced. So total torque will be sum of these 2 torques, because both are adding to each other, because this is also aiding in rotating like this, this is also aiding in rotating like this. So I am multiplying with 2. So total deflecting torque will be 2 times of BIL into N into B divided by 2. So 2 will cancel. It will become BIL into N into B. So this I can rearrange. I can write B into I into N into this L and B I am bringing together. L is the effective length of the conductor. B is the breadth or the distance between two sides of the coil. So that will give the area that is called as the face area of the coil in meter square. This A is nothing but face area of the coil in meter square, or otherwise, because once a coil is designed or once a machine is designed, once the instrument is designed, we know the flux density is constant, number of turns are constant, and L and B are also constant. That means dimensions will not change. Only variable will be current. So we can write it in the form some constant multiplied by the current. So that constant I am taking as a KD, which is nothing but in this case B into A into N. So from this we can conclude that the deflecting torque is proportional to current. So this deflecting torque can be increased either by increasing the value of B, or otherwise by increasing the number of turns of the coil. Either you increase the number of turns, that is one option. Second option is increase the flux density. If you are increasing the number of turns of the coil, automatically weight of your rotating system increases or weight of the moving system increases. When weight of the moving system increases, we have already discussed in our previous lectures, if the weight is increased, the friction also will increase and more torque is required for producing the required deflection. So that is the reason we want to keep the number of turns as minimum as possible. So better solution is to go for high flux density. That's why in practice we go for the magnetic material which are having more flux densities. Getting it? So now as the spring control is used in practice, so the control torque will be proportional to theta, or we have seen in the last class the controlling torque TC is equal to Kc multiplied by theta for the case of spring. So for the final deflection position, we know that deflection torque is equal to controlling torque. At that position, it will come to the stable position. So we can tell that on the final deflection position, Kd into I is equal to Kc into theta, or theta is equal to Kd by Kc into I. Or otherwise we can tell that theta is proportional to the current. So if you are in this case of PMMC instrument, the scale will be the linear scale. You can see here, this is the scale for the microammeter, PMMC type ammeter. You can see the scale is uniform throughout. That means the amount of distance the pointer will move per unit current will be same everywhere throughout the scale. We'll see in the next class that for the case of moving iron type of instruments, it is not uniform like this one. So now coming to the damping torque, because the damping torque is required, because once the deflection torque is applied, the pointer will start moving. So controlling torque will goes on increasing as the pointer is moving. When TD is equal to TC, it should come to the final steady state position. But due to moment of inertia, we have seen that will not stabilize at the final position. It will go on oscillating in the final position. So in order to dampen those oscillations, we need the damping torque. So here the damping torque is provided by eddy current damping using the aluminum former. So what is the derivation for the eddy current damping using aluminum former is already discussed in the previous lecture. So you can please refer to those lectures. So now I am proceeding further for the constructional details. If you are taking this instrument, I have opened the case here. So it will be something like this. This is my outer frame. So in this outer frame, you can see here, from here the poles are projected. So these are my poles. So poles will be here. So from these poles, the flux will pass from one pole to other. So in the center, if you are seeing from the side view, you will understand. So one spring is there. The spring is used for producing the controlling torque. And after the spring, this spring serves two purposes. One is the carrying the current from the external circuit to the moving coil, and second one providing the controlling torque also. Through the spring, it will go to the moving coil. The coil will be inside. So the coil, you can see here, this is represented here. This is the coil which will be inside. So through the coil, the current will pass. The coil is wound on one aluminum former. So if you want to see the details, it will look like this. If you are seeing from the side view, there is a north pole, there is a south pole. So inside there will be soft iron core will be there. The purpose of soft iron core is to provide the low reluctance path for the magnetic field. So that is the major purpose. So then above this core, we will make some small frame that is called as aluminum former. Above this aluminum former, we make the winding or moving coil. That coil is wound above the aluminum former. So this is kept in this one. So it is connected to pivot and jewel bearings. Through the pivot and jewel bearings, it is connected to this one. So here in practice, generally two control springs are used. One will be used on the top, one will be used on the bottom. So through one spring, the current will enter to the coil. Through another spring, it will come out. So providing two springs, generally they are wind in opposite directions so that the effect of temperature variations will be compensated. That means when the temperature is increased, generally length of the spring increases. So when the length of the spring is increased, automatically the tension increases in the spring, one spring. So as they are wound in the opposite direction, so one will expand in one direction, another one will expand in another direction. So the net resultant effect will be compensated. That is the reason they are wound in the opposite direction. So now coming to the pointer. So pointer, one side pointer will be there, and second side there will be one balancing weight. The purpose of the balancing weight is that your center of weight of your entire moving system will be in the center. So the effect of gravitational effect on your meter will be very less, or we can tell that the effect on these pivoted joints, because at this point it will be nearly pinpointed, because this entire moving system is lying on a small point in order to decrease the frictional loss. So that will not damage unnecessarily due to shifting in the weight. So for that purpose it is used. So now I am proceeding further. So if you are seeing from the top view, so from the top view I can represent like this. So this is my outer side frame is there. So there will be permanent magnets will be there on this side. So here one magnet will be there, here one magnet will be there. Permanent magnets are generally made up of alnico. So the disadvantage with this alnico and this type of material is they are very strong. So we cannot manufacture in the shape I want. We cannot grind in the shape I want. So for that what we will use, we will connect one soft iron core to this permanent magnet. So soft iron core is connected. So soft iron core we can make it as a concentric circle. Getting it? So inside there will be a iron core will be there. So above the iron core there will be aluminum former will be there here. Above the aluminum former there will be the coil that is wound. Getting it? So here this indicates the spring. So this indicates the pointer and the balancing weight. And here the scale will be there. So along with the scale there will be one more point I have forget to draw here. So this will be mirror also will be there. So mirror also used. This is used for avoiding the parallax error. So this we have already discussed in errors topic. You can please refer there if you have doubt. So along with that, one more thing is provided here. You can see here. So this knob is provided for zero balance. So you can see here that it is not coinciding with zero. So in order to adjust, do the zero adjustment, because with respect to the time due to aging of the spring, so the elasticity changes. So in order to compensate for that one or the zero adjustment, so this knob will be used. So that is the purpose of this one. So let us see each one of part in detail now. So first one I am starting with soft iron core. So soft iron core provides the low reluctance path for the flow of magnetic field. And second one, it provides the radial magnetic flux such that the force exerted on the coil is same at every point. And second one, aluminum former. This aluminum former provides the support for the coil. Also, it is used for providing the damping torque. I think up to here it is clear to you. So now coming to the pole. So the pole will have a permanent magnet, and along with that there will be soft iron core as well as one yoke also will be used. That yoke is also made up of the soft iron which will enclose the entire circle. Because when the flux is passing from, let us assume this is my north pole and this is the south pole. When the flux is passing from north pole to south pole, it will close its path through this yoke. So through the yoke it will pass. So now I am proceeding further. Pole shoe, this is called as the pole shoe. This pole shoe is made up of soft iron because it can be easily machined to the required shape. So it is used for providing the radial field. So next comes the soft iron yoke. It provides a return path for the flux and also provides the shielding from the stray external fields. So then coming to the moving coil. So the number of turns or thin insulated copper coil is usually wound on the aluminum former. And coming to the control springs, the control spring are the helical shaped control springs are used for providing the control torque, and the purpose serves the two purpose. One purpose is to provide the control torque and the second purpose is to lead the current in and out of the moving coil. But the disadvantage is, as these control springs are very thin springs, that means the thickness of these springs are very small or the cross-sectional area is very small, they cannot carry the more current. That means their current carrying capacity limits the current which can be safely carried by the moving coil. So it is limited to about 20 milliamperes because it cannot carry the more current. If you are passing more current, the springs will heat up and because of the temperature, so they will deteriorate. So the problem will come in the controlling torque. So in order to avoid this spoiling of the springs, so we have to limit that current to 20 milliamperes. So if you want to measure the current more than this value, what we have to do? We have to go for providing some shunt resistance across this coil. Let us take for example, I am representing my instrument like this. So through this instrument, the maximum current that can be passed is only 20 milliamperes. Let us assume I want to measure, for example, 1 ampere. If you want to measure 1 ampere, what we have to do? We will connect one resistance across this one so that the remaining current, that means 1 ampere minus 20 into 10 to the power of minus 3. So this much current will pass through this resistance. So this shunt resistance. So shunts are used for extending the range of the current. Similarly, the voltage drop across this, when 20 milliamperes is passing, the voltage drop across this will be around 100 millivolts. That means the voltage drop across this meter is 100 millivolts. That means if you are connecting this meter directly to 100 millivolt supply, the current that is drawn by the meter will be 20 milliampere only. But if you want to use it for higher voltages, so what we have to do? We have to connect some series resistance. So some series resistance will be connected in series with the meter, so that the current will be limited to 20 milliamperes only. So in order to limit the current to 20 milliamperes, generally a series resistor will be used. If the voltage is greater than, so your supply voltage is greater than 100 millivolts. So in that case, it will be done like this. So that same thing I am extending here. So to extend the range of the ammeter, shunt resistors are used to bypass the current. So they are called as shunts. And similarly, to extend the range of the voltmeter, series resistor, also called as multiplier, is used to limit the current to the safe value. So detailed analysis and design of the shunts and series will be discussed in the next class with numerical. So there I will discuss in detail. So now coming to the errors in the PMMC instrument. So first error can be happen due to weakening of the permanent magnets with aging. So with the respect to change in the time, the magnets will go on losing its magnetization properties. So in order to avoid this, what will be there, at the time of manufacturing of the magnets only, the magnets are aged. So we will create the artificial aging by heating and vibration treatment. So using this treatment, whichever magnetic field will be lost with respect to the time, all those magnetic field will be lost from this. And this process results in the loss of initial magnetism, but whichever magnetic field that is remaining, that will remain for nearly lifetime. So using this, we can avoid the weakening of the permanent magnets with respect to the aging. And second one, the weakening of the springs due to aging and temperature effect. Due to the aging, what happens, the property of the material will goes on changing. So automatically it loses its elasticity property with respect to the aging. And second is the effect of the temperature rise on the springs. So when the temperature is raised, then the length of the spring changes. When the length of the spring changes, automatically the spring tension also changes, or the controlling torque also will change. These are the two things you have to remember. So in order to avoid this problem, what we will do, proper material is selected such as the phosphor bronze, and to reduce the temperature effect to some lesser extent, two spiral springs are wound in the opposite direction so that it will be compensated easily. But in practice, it is observed that for 1 degree centigrade rise in the temperature, it reduces the strength of the springs by about 0.04%. Accordingly, the care should be taken. That also we are going to discuss how that can be avoided. So now coming to change in the resistance of the moving coil. So as the coil is made up of copper, it is affected by the temperature variations, because we know that whenever current is passing through the coil, so I square R losses are produced. So because of the I square R losses, temperature increases inside the meter. So when the temperature increases, we know copper is having positive temperature coefficient of resistance. So the resistance increases with change in the temperature. So automatically the amount of current drawn from the supply will change. So automatically meter reading is affected. So in order to avoid this problem, what we do, so a resistor of low temperature coefficient, which is called as the swamping resistor, is connected in series with the coil. So this swamping resistor is made up of manganese. The material is manganese, which is having 0 temperature coefficient of resistance. Generally, this is combined with the copper in the ratio of 20:1 to 30:1. That means the 20 times manganese and 1 time copper, like this in this ratio, or 30:1 ratio, generally we mix them, and that material is used for designing the swamping resistor. So the total resistance of the coil plus the swamping resistor, because both are connected now in series, increases slightly with the temperature, but it is just enough to counteract the change of the springs and the magnet, because we have told that with respect to the time, the magnets loses its magnetizing property and the spring loses its tension, but that will be counterbalanced by the rise in the resistance of the coil and the swamping resistor, because of the rise in this resistance of the coil, the current drawn by the coil decreases. So automatically we have seen that the torque equation, it will be equal to B into I into L. So current will decrease. So when the current will decrease, so automatically torque decreases. But at the same time, with the rise in the temperature, the B decreases. So it will be compensated there, and remaining part is compensating for the effect of change in the springs with respect to change in the temperature. Getting it? So by using the swamping resistor, all the above disadvantages will be compensated completely. So the design considerations will be taken care. So now let us see the advantages and disadvantages. The advantage is it consumes very less power, because in order to produce the torque, two things will be required. One, magnetic flux is required, and second one, the current is required. Because in this case, the magnetic flux required is supplied by the permanent magnet. So the amount of current required to produce the given torque is very less. We are going to see in detail in the coming lectures that in some type of instrument, both the flux as well as current, that means entire torque will be produced due to the current only. So in that case, more power consumption will be there. So in this case, the power consumption will be 25 microwatt to 200 microwatts. And second one, it is very accurate and reliable type of instrument, and the scales are uniform up to 270 degrees or more. Up to 270 degrees also we can use, because we are going for the spring control. It is not limited to 90 degrees. We have seen in our previous lectures, if you are going for gravity control, it is limited to 90 degrees. But here it can go up to 270 degrees. And second one, we have proved that it will have the uniform scale. And then it will have high torque by weight ratio. That means for a given weight of this instrument, the torque produced will be more in this instrument. Again, this is also due to this permanent magnet, because we can increase the magnetic flux density easily. So very effective built-in damping is provided here, because using this eddy current damping, and no effect of stray magnetic fields because of the stray magnet, because already a strong magnetic field is employed. Already the magnetic field produced by the permanent magnet is very strong compared to external magnetic fields. So that's why it is not affected by the external stray magnetic fields. So now coming to the disadvantages, this cannot be used for direct AC current measurement. In the case of AC current, we know that the current will oscillate like this. During positive half cycle, it will be in one direction. Negative half cycle, it will be in another direction. That means during positive half cycle, if you are taking this conductor, your conductor is lying here. So one half cycle, it is dot. So the torque will be produced in this direction. So another half cycle, this dot becomes cross. So the direction of the torque will be opposite. That means every half cycle, the direction of the torque is changing. So due to moment of inertia of the rotor, it cannot vary that much fast. Because if you are taking 50 Hz supply, so it will vary. One cycle will complete in 1/50th of a second. It is completing one cycle, and one half cycle is completing in this half of the time only. So that much less time it is completing. So that much fast it cannot change. So that's why it will not move for the case of AC. So, and second one, it is costlier than that of moving iron instrument. And the coil being very fine, so it cannot withstand prolonged overloading. So proper care should be taken care that it will not be overloaded. Particularly we are going to see in the next class, when you are going for the multi-range ammeter or multi-range voltmeter, by mistake if you connect the ammeter in the lower range but give the current corresponding to the higher range, it may damage your instrument. Similar is the case, it is kept for the lower voltage measurement. Corresponding to lower voltage, you connect to the higher voltage, more current will pass through the coil and the coil may damage. So that care should be taken care for PMMC instrument. I hope the basic working principle of PMMC instrument and construction is clear to you, and what is the application of shunts and multipliers for extending the range of ammeters and voltmeters will be discussed in the next class. So thank you very much.